When you think of a manufacturing floor, you probably picture something like this: massive steel presses, cranes swinging overhead, and thousands of parts moving at breakneck speed. But at the absolute bleeding edge of technology, the assembly line slows to a crawl. Here, a robotic arm creeps forward not in feet per second, but in nanometers. If that arm overshoots its target by a single millimeter, it doesn't mean a defective product. It means the catastrophic failure of a machine worth nearly $500 million. In this room, the ultimate goal reaches past production speed. The true engineering marvel is achieving perfect, immovable physical stasis. You are looking at one of the most controlled environments on Earth. Notice how deliberately the technicians move in their protective suits, treating the space less like a factory floor and more like a surgical theater. They are assembling the high-NA EUV. It is the only machine capable of manufacturing the next generation of microchips that power our global economy. To achieve that, it has to manipulate light on a scale so tiny that we are essentially pushing against the hard limits of physics. This facility functions as a laboratory, engineered to test the fundamental boundaries of physical reality. Before those technicians can even tighten the first bolt, parts arrive from a decentralized network. Over 5,100 separate companies build highly specialized components for this one system. Look at the sheer volume of these freight yards. It takes 40 of these massive shipping containers to hold pieces for a single machine. Because time and vibration are constant threats, marine shipping isn't enough. Moving that much delicate hardware requires 3 fully loaded Boeing 747 cargo planes. The real assembly line actually begins thousands of miles away, acting as a global nervous system, where every single shipment must converge in one room at the exact right moment. At the core of the system are optical components like this. These curved, intricate lenses and mirrors are responsible for catching extreme ultraviolet light. This 3D diagram shows the level of precision we are dealing with. If you scaled one of these mirrors up to the size of Germany, the tallest bump would be exactly 1 millimeter high. Because the surface is impossibly smooth, a single stray speck of dust landing on it acts like a boulder. It shatters the precise geometry of the light beam and renders the machine useless. Polishing the mirror is difficult enough, but the true engineering nightmare is isolating that flawless surface from a world that is constantly vibrating and shifting. The greatest threat inside the cleanroom is completely invisible. It is the microscopic seismic rumbling traveling through the Earth's crust, often caused by something as simple as a massive transport truck driving down a highway several miles away. This wireframe schematic reveals exactly how the system fights back. Notice the glowing lower network. That is the metrology layer. It is a dense web of sensors designed to detect incoming waves. As the ground moves, the machine's suspension legs physically adjust and neutralize those frequencies 20,000 times every second. All of this frantic, invisible stabilization has one purpose: keeping the system perfectly steady, so a laser inside a total vacuum can hit a microscopic drop of molten tin 50,000 times per second. The entire assembly line functions as a living, dynamic suspension system, perpetually counteracting the Earth's natural motion. 5,000 global suppliers, perfectly polished mirrors, and a sensor network making microscopic adjustments thousands of times a second, all converging into a single functional unit. This machine has reached a cognitive threshold where its 5,000 subsystems are so deeply interconnected that no single mind can map the entire machine. Its coordination exceeds the limit of human comprehension. Historically, the craftsman directed the movement of the tool. Here, the machine performs its own impossible alignment, while the humans exist primarily so the hardware can function. By pushing engineering to this extreme, we have created a bottleneck for modern civilization. The machine now defines the hard limits of what we can create.